I'm Erica Boffman with Molly Galloway and Cameron Latke. Our project this fall is to analyze the adoption of electric vehicles in the United States by the year 2040. We want to use a mathematical model to determine if the U.S. energy production can withstand the increase in consumption to power a full fleet of electric passenger vehicles, and we want to know if converting our fleet of vehicles alone will help us meet the Paris Agreement. There are more than 250 million vehicles in the United States. The majority of these vehicles use an internal combustion engine, or an ICE. ICEs combust fossil fuels that release carbon dioxide gases into the atmosphere. The buildup of CO2 gases is causing the Earth's atmosphere to warm, resulting in changes to the climate that we see today. Electric vehicles, or EVs, use electricity as their fuel and emit no tailpipe emissions. Vehicles, or PHEVs, are hybrid electric vehicles of an internal combustion engine and an electric motor. Emit CO2 gases, but at a slower rate than ICE vehicles. Several countries, including Britain and France, have integrated a ban on ICE vehicles by the year 2040. In this project, we will propose that the U.S. could do the same through the combined use of EVs and PHEVs. Converting the U.S. fleet of vehicles to these forms could dramatically reduce carbon emissions and help us meet our requirements to the Paris Agreement. So, what will the electrical consumption and emissions rate look like in 2040? We derived a mathematical model to calculate these variables, but we needed to make a few predictions to simplify our calculations. First, for our model, we assumed that no ICE vehicles will be in operation. All vehicles will either be electric or a plug-in hybrid. We assumed that charging would occur at night during off-peak hours to prevent any strain on the power grid. We used a linear model to predict the total number of vehicles in 2040, and we concluded that the transportation sector would reduce carbon dioxide emissions at the same rate as the energy sector.
After analyzing the growth of registered vehicles going back 20 years, we were able to derive a linear model. Extrapolating off of this linear model, we found that there would be approximately 335 million vehicles in use by the year 2040. And from the derived equation you can see here, we set the x value to be 45 years. The Paris Agreement doesn't specify exactly how much the U.S. needs to reduce its carbon footprint by the year 2040 in order to meet the agreement, but there are many estimates out there that attempt to find carbon emission guidelines. One paper in particular, published this year in Science magazine, gave a detailed roadmap the U.S. must follow in order to stay on course for the Paris goals. According to the paper, starting in 2020, emissions from the energy industry must fall in half each decade. The paper did not give any guidelines for the transportation sector, but we can make the reasonable assumption that the transportation industry must see its emission follow the same trajectory as the energy sector. With this in mind, what we first needed to do was calculate the current carbon emissions that come from the transportation sector as a whole, and this is illustrated by the graph you see here. Then, we took the percent of that sector that just comes from vehicles. And finally, by dividing this emissions number in half each decade until the year 2040, we obtained a final emissions target of 375 million tons of CO2 per year by the year 2040. And here's a graph from the paper published in Science magazine that shows the emission guidelines I mentioned earlier. You can see that there are additional measures that need to be taken, including the reduction of carbon emissions from land use and the increase of carbon capture technologies.
In order to calculate the number of EVs and plug-in hybrids, we set up the following equations where the underlying variables are unknowns. First, all 335 million cars in 2040A consist of either electric cars E or hybrid cars F. Secondly, total CO2 emissions per year in metric tons C are equal to the number of hybrids F times the yearly emissions that hybrids produce, G, which is 2.215 metric tons per hybrid. Lastly, total yearly electricity use in kilowatt hours D is then equal to the number of EVs and the number of hybrids times the annual amount of electricity required to fuel them. Since average distance traveled per car every year is 13,476 miles, it takes about 4,582 kilowatt hours a year to power one electric car and about 2,749 kilowatt hours a year to power a hybrid, where electric cars require only electricity to run and hybrids run 60% on electricity. We created a system of equations because we wanted to know the total emissions produced and the amount of electricity used by both hybrids and electric cars in some optimal ratio. Since the number of each are required in calculations for total emissions and electricity use, we thought a system of equations was most appropriate. From our system of three equations, we created a single equation to find the total amount of electricity used by all vehicles per year in 2040. Since we had four unknowns, total emissions, electricity use, and the number of EVs and hybrids in use in 2040, we used substitution to refine and solve the model. This was done by solving the second equation for F to get C divided by G, and replacing that value for F into equation 1, which shows the number of electric vehicles is equal to A minus C divided by G, or all vehicles minus the number of hybrids. We then replace these new values for E and F into the third equation to give us a formula for D, the annual amount of electricity used. We can find this so long as we determine the value of C, the target annual carbon emissions for 2040. This final equation makes sense if you break down the variables. It basically tells us that the annual power used by all cars in 2040 is equal to the annual power used if all cars were electric, minus annual power used if all hybrids were purely electric, plus the actual annual power consumed by hybrids. We decided to make the limiting factor in our model the maximum CO2 emissions allowed in order to meet the Paris Agreement, but C can vary based on any limit of CO2 emissions. Following the model we set up, if our goal is 375 million CO2 emissions, and there will be about 335 million cars in 2040, then we estimate the minimum number of EVs in 2040 need to be 165.7 million, along with 169.3 million hybrids. This would require 1.2 trillion kilowatt hours of power grid capacity, which is roughly a 30% increase from the current US production of 4.08 trillion kilowatt hours. Because increases in energy production in recent decades have been pretty modest, the US would need to work towards supplying this much extra power.
In this graph, we represented our mathematical model of electrical consumption and carbon emissions versus the total number of electric vehicles. You can see the blue line plots the electricity consumption, and the red line plots the emissions rate. By using a target emissions rate of 375 million metric tons, we found our value for EVs at 165.7 million. This graph can also be used to calculate the optimal number of EVs using any limiting factor for emissions or electrical consumption. So how does our model perform? We found in our calculations that the US would need an additional 1.2 trillion kilowatt hours to meet vehicle power needs in 2040. Other sources that we looked at estimated the power consumption to grow 0.746 trillion kilowatt hours, meaning that their estimates are more conservative than ours. This difference may be due to predictions in technology improvements or to an increased use of public transportation. In our model, we found that the US fleet of vehicles will be made up of nearly half EVs and half PHEVs. This helped us to calculate a reduction of 126.8 billion gallons of gasoline annually. Overall, our model is very versatile. It gives a lot of information based on only a few variables. It can be used in any future year estimates, given a goal of carbon dioxide emissions or electrical consumption. However, we feel that our model does fall short, given our assumption that all cars in 2040 will either be electric or plug-in hybrid. The technology advancements in vehicle production and the use of renewable energy sources continue to improve. The expense of these advancements will have an effect on the purchasing power of most Americans. We would like to see improved predictions in our model for changes to the power grid between now and 2040, for changes in overall electricity consumption, for improvements in battery and vehicle technology, and for changes in methods of transportation. And we would like to see continued research into the feasibility of EVs and the reduction of greenhouse gases. We sincerely thank you for your time, and we encourage you to go out and see what you can do to improve our environment.
We got the whole